Welcome, my digital pathology trailblazers. I am so excited to finally be able to give you the book, Digital Pathology One-on-One, everything you need to know to start and continue your digital pathology journey. If you've been following me on social media recently, in the recent, I don't know how many months, because actually it was supposed to come out several months ago, but finally now, October 2023, the book is out. You voted on the title, you voted on the cover, so I'm super appreciative of that. And you join me for the webinar launch. I'm going to leave the link to the replay of the launch in the show notes so that anybody who didn't make it and wants to see the webinar, where I also teach on a little bit why digital pathology is the way pathology is going to be done, and where I see signs of that. And it's going to be really fast. It's not going to be, in the next 20 years. It's going to be in the next 5. Although in my recent podcast, Dr. Anil Parwani, he was saying that he thought that in 2003, that everybody's going to be digital by 2007. So he was pretty optimistic, but I'm even more optimistic that now is the time. That means that everybody needs to get the info that is included in this book. That's why there is a free PDF version, link in the show notes. There is this podcast, which is the free audio version. And for everybody who needs a different form, there is already an Amazon Kindle version available, paperback, hardcover, and we also are going to be preparing a video course on the contents of this book. But for now, the first chapter of the audio version. Let's dive into it.
Learn about the newest digital pathology trends in science and industry, meet the most interesting people in the niche, and gain insights relevant to your own projects. Here is where pathology meets computer science. You are listening to the Digital Pathology Podcast with your host, Dr. Alexandra Zhurav.
Digital Pathology 101. All you need to know to start and continue your digital pathology journey. Written by Alexandra Zhurav. Read by Alexandra Zhurav. About the author. Great to see you. I'm Alexandra Zhurav and I'm here to help you do better digital pathology. Better digital pathology? What do you mean by that, Alex? I mean, help you understand what digital pathology is, what is its place in pathology and healthcare, as well as give you all the information you need to be part of the digital pathology revolution, even if you are just starting. I am a board-certified veterinary pathologist with a PhD in infectious pathology, as well as the CEO of the Digital Pathology Place and the host of the Digital Pathology Podcast. At digitalpathologyplace.com, I share knowledge gained during my work with image analysis engineers, quality control and regulatory experts, as well as academic and industry partners. I try to bring in new experts and share new insights with each podcast episode. Basically, I try to bring the complex digital pathology topics to as many people as possible in as clear of a way as possible. I do it to build a bridge between pathology and computer science necessary to advance digital pathology as a discipline and to help you accelerate your digital pathology efforts. Building this bridge started with my first job after my residency. I was fortunate to work in a digital pathology company where I was the pathologist supporting a team of tissue image analysis scientists. I remember going into one of my first meetings on the job and then frantically going through my notes, trying to look confident, but not entirely sure what the non-pathologists were talking about. I knew the pathology part, but I quickly realized that I needed to learn about computer vision, software development, and general digital pathology principles to the same degree as my image analysis colleagues needed to learn about pathology. So I started putting together presentations and lectures and writing articles on digital pathology relevant topics. At the beginning, it was intended for my immediate collaborators, but with time, my audience as well as the demand for this information grew significantly. Now, knowing the potential digital pathology has to improve the drug development process and patient care, I'm on a mission to accelerate your digital pathology journey. Truly yours, Alexandra Zhurav, DVM, PhD, Diplomate, ACVP. Preface. Welcome to this beginner's guide to digital pathology, a synthesis of countless lectures, webinars, and presentations I've delivered to diverse audiences embarking on their journey in this dynamic field. This includes veterinary and medical pathologists, digital pathology vendors, sales professionals, validation experts, product managers, and many, many more, all with one thing in common: the curiosity and courage to venture into the dynamic field of digital pathology. Whether you're just starting out or are already established in this arena, this book aims to provide valuable insights and knowledge that will enhance your understanding and implementation of digital pathology. Our journey spans a broad range of topics, from image acquisition, storage, and analysis to understanding the regulatory landscape, along with the challenges and benefits this technology presents. This guide isn't designed as a peer-reviewed scientific publication, but rather as a friendly manual to help you ignite your journey into the world of digital pathology. Drawing upon a decade's worth of industry experience, this book is designed to provide all the essential elements needed to propel you forward on your path. While the self-published guide doesn't contain specific references for every piece of included information, barring a few exceptions, rest assured that I have painstakingly fact-checked and personally tested each piece of advice and example found within these pages. My hope is that after reading this guide, you'll feel prepared to confidently contribute your unique expertise to any digital pathology initiative. This book aims to provide you with a robust foundational knowledge, a springboard from which you can continue to build and expand your understanding. From interpreting the nuances of high-resolution digital images with advanced software tools, to understanding the importance of quality control of image analysis results, the power and potential of digital pathology will unfurl before you. Should you find yourself thirsting for more in-depth information on any of the topics touched upon in this book, I encourage you to visit the Digital Pathology Club at digitalpathology.club. Here you'll find all of my digital pathology courses, a vibrant community, and new resources added every month. I'd be delighted to welcome you into our community of digital pathology trailblazers. Finally, I hope you enjoyed the journey this book takes you on. Your feedback is always appreciated, so don't hesitate to connect with me on LinkedIn and kickstart the conversation. Here's to your digital pathology journey. Happy reading and happy digital pathology trailblazing. Introduction. What is digital pathology and why it matters? The world of pathology has undergone a significant transformation in recent years with the advent of digital pathology. This technology has enabled pathologists to digitize glass slides and access them from anywhere, allowing for improved access to care, greater workflow efficiency, and streamlined remote collaboration in diagnosing diseases and advancing biomedical research. The benefits of digital pathology are clear, but for many professionals, navigating this new territory can be daunting. That's where this book comes in. Before we dive into the technical details, let me tell you a bit about my beginnings and first steps in digital pathology. I'm originally from Poland, but went to do my veterinary pathology residency in Germany. And as a veterinary pathology resident in Germany, I was tasked with teaching vet students histopathology. During my introductions before the semester started, I heard from my colleagues that it was sometimes okay if a student wouldn't attend the lecture because they could check the slides later. I didn't understand it at first. What did they mean by later? I had the slides in front of me ready to teach, go back and forth with them on the microscope and show them any cell they wanted. But I wasn't about to schedule a special session just for this one student that missed a class. I had my own stuff to deal with. Soon enough, to my amazement, I discovered that these students had access to a portal where they could look at scanned slides and learn at their own pace. I thought this was a great tool, and I was very envious of their resources, as I had not had access to this technology during my veterinary education in Poland in the early 2000s. After finishing my residency, I joined a digital pathology startup where I was responsible for teaching pathology to tissue image analysis scientists. However, I was not supposed to teach them all the aspects of pathology as I did with the students during my residency. This time, I was only supposed to teach just the aspects relevant to their job, and their job was to design computer algorithms to analyze tissue. The job was tricky because it wasn't just teaching. I needed to first figure out what exactly needed to be taught to them. And for that, I needed to learn all the computer science and computer vision aspects of digital pathology relevant to their job. This was a steep learning curve. I struggled to match my pathology knowledge to their computer vision tasks involved in image analysis, piecing together information like a jigsaw puzzle without knowing what the complete picture was supposed to look like. But eventually, through trial and error, I figured it out, and the framework I was previously missing emerged from my self-study and problem solving, and I was able to develop an organized way of learning that will allow me to understand the subject matter more comprehensively. I want to share with you that framework together with what I learned along the way and provide you with the missing pieces of the digital pathology puzzle you might still be trying to put in the right places of the whole picture. I also have a personal relationship with pathology, which was taken to a whole new level once I discovered digital pathology. I chose the specialty of pathology to have location freedom. I have always loved to travel and explore the world. I started as a practicing veterinarian, but after a few years, it was clear to me that this path was not so compatible with the world exploration dreams I had at that time. I remember at one point I had an opportunity to spend some time in Australia, as we had family living there temporarily, but it turned out it wasn't that easy for me to start working in the land of kangaroos, that I needed a license and wasn't able to get it in a short period of time. In the end, I was not able to go, and in the process, I realized that I would need to get licensed as a veterinarian everywhere I went. I felt like I missed my chance to explore something new and unique, and I didn't want it to happen to me again, so I decided to pivot. I liked pathology in vet school, and when I discovered it could actually be a full-time veterinary career and not just an interesting course I took, the choice was made. I figured that with an internationally recognized board certification, I would be able to work in most of the countries. That was location freedom to me at that time. Little did I know that this term will gain a whole new meaning after the COVID-19 pandemic, and that remote work will become far more mainstream than I have ever imagined. Remote pathology work would be possible even without digitization of slides. With this technological capability, it entered a new dimension. In my pursuit of pathology education, ended up in the USA, which is the 6th country I have lived in, but my family stayed in Poland, where I was born. Of course, I want to see them as often as possible, and I want my 2 sons, 2 and 4 years old at the time of writing this book, to experience Poland for real, to be able to get to know the country, have a close relationship with their grandma and their aunts and cousins, and have their own Polish friends. This is only possible if we actually spend time there. And this is where the super personal relationship with digital pathology enters the picture. Thanks to digital pathology, I am able to travel to Poland and spend several weeks at a time, several times a year there without losing my job continuity. Equipped with my laptop, decent internet, and a good computer screen, I am able to provide pathology evaluation from practically every place on the planet, including my little village in Poland. And this is something I am extremely grateful for. I hope digital pathology will become an equally impactful tool for you personally and for your mission of improving patient care and advancing science. In this book, we will explore the basics of digital pathology, including the benefits and limitations of this technology, how to prepare slides for digital scanning, and the tools and software needed to analyze and interpret digital slides. We will also examine some of the practical applications of digital pathology, such as teleconsultation and image analysis. This book is intended for anyone interested in learning about digital pathology, whether you are just starting your journey or looking to expand your knowledge. While the subject matter may be technical at times, I hope that by the end of this book, you will feel confident in your understanding of digital pathology and be able to confidently participate in digital pathology-related discussions and apply the technology in your work. I'll take you on a journey through the digital pathology milestones, its basic concepts, as well as image analysis now supercharged by the integration of artificial intelligence and machine learning. This book is divided into 3 parts. In part 1, we'll explore the history and evolution of digital pathology and discuss the fundamental concept of digitization. Part 2 delves into image analysis, which has transformed digital pathology into a more powerful and attractive technology. We'll also explore how artificial intelligence and machine learning have become integral components of digital pathology. Finally, in part 3, we'll focus on digital pathology and good laboratory practice. As a veterinary pathologist working in non-clinical settings, I'll share my experience with the GLP regulatory framework and how these concepts apply to other regulatory frameworks as well. By the end of this book, you'll have a comprehensive understanding of digital pathology and its many applications. You're going to get the tools you need to stay on top of the latest trends in this exciting field. So let's start by exploring the milestones and basic concepts that have brought digital pathology to where it is today. Chapter 1: Digital Pathology Milestones and Basic Digitalization Concepts. In this chapter, we will take a closer look at the fundamental concepts that laid the foundation for the development of digital pathology. It all started with telepathology, the concept of being able to do pathology remotely. However, digital pathology did not start as digital at all. Instead, it began in an analog format. Nonetheless, the potential of remote pathology initiated the development of digital pathology. We will go through the various historical milestones that have shaped the digital pathology field. I have divided these milestones into two categories: historical and regulatory milestones. We will start by exploring the historical milestones and answering the questions of when digital pathology began. By understanding the historical context of digital pathology, you will be better equipped to understand how it has evolved and what the future holds. So let's dive into the past and explore the beginnings of digital pathology. Digital pathology milestones. A. Historical milestones. The history of digital pathology dates back to 1986, when Dr. Ronald Weinstein's telepathology system and the term telepathology was introduced to the public. Telepathology. The term telepathology is a portmanteau of telecommunications and pathology, signifying the use of telecommunications technology to facilitate the transfer of pathology image-rich data for diagnosis, education, and research. The seeds of this remarkable technology were sown in the late 20th century, in an era where the concept of transmitting medical images over long distances was a novelty. Telepathology was born out of necessity, due to the geographical dispersion of patients and the limited availability of pathologists, especially in remote areas. Before the advent of this technology, tissue samples had to be physically transported for diagnosis, which was both time-consuming and could result in the degradation of samples. Telepathology helped to eliminate these challenges by enabling the transfer of digital images of pathology slides to pathologists located elsewhere for timely and accurate diagnosis. The first pathology system came into being due to the vision and perseverance of Dr. Ronald S. Weinstein. In 1986, Dr. Weinstein, a pathologist and an early visionary in telemedicine, coined the term telepathology and envisioned its potential to revolutionize the field of pathology. It was born out of pressing necessity for swift remote consultations. This revolutionary idea took form in the 1980s, catalyzed by startling data from the National Bladder Cancer Project, NBCP. The findings from this multi-institutional clinical trial across the United States revealed significant discrepancies in diagnosis, compelling Dr. Weinstein, the director of the Central Pathology Laboratory, CPL, for NBCP, to develop a system for uropathologists at the CPL to examine patient data from the participating institutions. Nonetheless, the slim window between surgery and inclusion in clinical trials, coupled with the inadequate technological infrastructure for real-time remote pathology, posed a challenge. The answer lay in the emergence of dynamic robotic telepathology. Dynamic robotic microscopy, commercialized for the first time in 1985, involves a satellite-controlled microscope that facilitates remote slide evaluation. This innovative tool was the first of its kind, enabling remote pathology and sparking a wave of technological evolution that continues to unfold. Dr. Weinstein not only devised but also popularized the term telepathology to define the scope of this groundbreaking technology. His unveiling of this concept at the Armed Force Institute of Pathology, AFIP, in 1986 makes a significant milestone in the history of telepathology. The same year also witnessed the first public demonstration of the robotic microscope. A pathologist based in Washington, D.C., remotely controlled a microscope stationed about 2,000 miles away in El Paso, Texas, to evaluate and diagnose a breath biopsy. This landmark event was a resounding success, marking a hopeful and promising beginning for a novel medical field. The maturation of telepathology into what we now know as digital pathology is a testament to continuous innovation, adoption, and adaptation over the decades. One of the earliest real-world applications of telepathology came in 1989, when a network was set up in northern Norway to offer frozen section services to 5 remote hospitals, thus addressing the challenges of distance and speed. I hope you're enjoying the read so far. Just a quick reminder, if you know anybody who wants to learn more or start learning about digital pathology, please share this book with them. It's for free as PDF, it's for free as this podcast. I will very much appreciate it. And now back to the episode. First commercialization attempts. Fast forward to 1994, commercialization began to take shape with hardware for a complete analog dynamic robotic telepathology system becoming available for purchase. This marked the transition of telepathology from a concept into a commercial reality, which, by the way, I think is crucial for the advancement of any technology. Then in 1995, the AFIP embraced the future by starting a telepathology consult service primarily using static images. This represented an important endorsement of the technology from a prestigious institution. Telepathology advances, whole slide scanners. At the dawn of the new millennium, in the year 2000, the technology leapt forward with the introduction of whole slide imaging, WSI, and whole slide scanners to the market. This sparked validation efforts for clinical digital pathology applications, marking a pivotal moment in the evolution of the field. Further institutional adoption came in 2001 when the U.S. Army telemedicine program started utilizing dynamic telepathology, demonstrating the practical and strategic value of this technology. By 2005, they transitioned from using static images for consults to whole slide images, highlighting the rapid evolution and acceptance of this technology. Coordinated efforts. In 2009, the Digital Pathology Association, DPA, was formed, marking an important milestone in the recognition and establishment of this emerging field. This was followed in 2011 by the creation of a telepathology network in eastern Quebec, Canada, further demonstrating the technology's global reach and acceptance. Notably, the reach of digital pathology expanded beyond human medicine. In 2014, IDEX became the first veterinary diagnostic laboratory to embrace digital technology and provide remote veterinary pathology diagnosis. This milestone, achieved by veterinary pathologists, paved the way for human pathologists, and it happened 3 years before the first system for human pathology primary diagnosis was officially approved by the FDA. This journey from the initial real-world application of telepathology in Norway to its implementation in veterinary pathology illustrates the growth and scope of this transformative technology. As we move forward, the innovations and adaptations within digital pathology continue and redefine the landscape of pathology services. B. Regulatory milestones. After COVID-19 pandemic, remote work became a lot more mainstream, and we are all bombarded with images of laptop entrepreneurs through all the social media channels. Could a pathologist also work from anywhere? In theory, yes. In practice, pathology work takes place in a regulated environment, and it happens for a reason. Regulatory restrictions, the impact of the pap mill scandal. A notable event that significantly affected the field of telepathology was the pap mill scandal in the late 1980s. This incident led to a significant regulatory response, which in turn shaped the landscape of pathology and, by extension, telepathology. The pap mill scandal involved the discovery that certain pathology labs, dubbed pap mills, were processing an extraordinary high volume of pap smears, which are tests for cervical cancer, with little oversight and often inadequate review. The lack of stringent quality control standards resulted in many false negatives, meaning that numerous women were incorrectly informed that they did not have precancerous or cancerous conditions when in fact they did. This led to a public outcry and a significant loss of trust in the field. In response to this scandal, the U.S. Congress passed the Clinical Laboratory Improvement Amendments, CLIA, in 1988. The CLIA regulations significantly increased federal oversight of laboratories, requiring labs to be certified by the state as well as the Center for Medicare and Medicaid Services, CMS, or a private accreditation agency approved by CMS. One of the key provisions of the CLIA regulation that had direct implication for telepathology was the requirement that pathologists must sign off on cases from a CLIA-certified location. This means that the pathologist cannot simply review and sign off on cases from any location. Instead, the location from which they review cases must meet the CLIA standards for certification, which involve strict requirements for quality assurance, personal qualifications, and documentation. This regulation presented a challenge for the early development of telepathology, as it imposed restrictions on where telepathology could be practiced. It also raised questions about how to ensure the quality and security of digital data transmitted across different locations. Despite the regulatory challenges, the CLIA regulations helped to restore public trust in pathology services by improving the quality and reliability of lab results. They also prompted the telepathology field to invest in technological solutions to ensure secure, reliable, and high-quality digital data transformation, which ultimately has been essential to the development and widespread adoption of telepathology. Today, the regulatory landscape continues to evolve, and with advances in technology and the increased use of telepathology, there is ongoing discussion about potential updates to the CLIA regulation to accommodate these changes while maintaining high standards for patient safety and care quality. In 1999, the American Telepathology Association laid the groundwork for standardizing telepathology practices by establishing the first set of comprehensive guidelines, which were updated in 2014. Central to these guidelines were 5 pivotal principles. 1. Technological standards, which ensured secure, reliable transmission of high-resolution images and patient data. 2. Personal training, emphasizing the need for proficiency in technical and clinical aspects of telepathology. 3. Quality assurance, advocating for routine maintenance and regular assessments of image quality. 4. Data security and patient confidentiality, underlining the importance of encryption and Health Insurance Portability and Accountability Act, HIPAA compliance. 5. Regulatory compliance, reinforcing adherence to regulations like CLIA. These guidelines, while later in 2014 refined and expanded, still serve as a foundational pillar in the practice of telepathology, emphasizing quality of care and professionalism. Image analysis algorithms. In the early 2000s, the first whole-slide image scanners were introduced to the market, and it was possible to digital whole glass slides. This gave the researchers the ability to develop and apply computer algorithms to pathology images. This was especially beneficial for quantification of immunohistochemistry biomarkers, and several algorithms were developed to help pathologists with this daunting task. In 2003, FDA granted clearance to the first algorithms for quantitative image analysis of IHC markers. Estrogen receptor ER quantification tool by cell analysis and human epidermal growth factor receptor 2, HER2, quantification tool by Clarient received clearance, marking the entry into the market as medical devices. New telepathology guidelines. A decade later, in 2013, the Royal College of Pathologists in Great Britain took a key step by establishing official telepathology guidelines. This represented a significant move towards standardizing telepathology practices and set the stage for similar actions by other professional bodies. The following year, 2014, saw the Canadian Association of Pathologists issuing telepathology guidelines and the American Telepathology Association updating its 1999 guidelines. These actions further emphasize the importance of maintaining high professional standards in telepathology. Whole slide images for primary diagnosis. In a landmark move, the FDA approved whole slide imaging for primary diagnosis in surgical pathology in 2017, with the Philips Intelsite system approved as a Class II medical device. This represented a significant endorsement of digital pathology by a major regulatory body. The FDA followed this by granting Leica Biosystems 510(k) clearance for the Aperio 82DX system in 2019 and Hamamatsu Photonics for their NanoZoomer S360 MD slide scanner in 2022. In response to the pandemic, 2020 also saw significant regulatory flexibility in response to the COVID-19 pandemic. In March, the Centers for Medicaid and Medicare Services, CMS, issued a memorandum temporarily allowing pathologists to review pathology slides remotely from non-CLIA certified locations during the pandemic, subject to certain conditions. In April 2020, the FDA issued an enforcement policy for remote digital pathology devices during the pandemic. This temporary measure allowed for the use of different digital pathology hardware and software, even those not approved or cleared as medical devices, provided that an internal validation was performed at the institution using the devices. The COVID-19 pandemic is over, and on May 11, 2023, CLIA issued Post-Public Health Emergency, PHE, guidance taking back some remote work privileges. During the PHE, CMS allowed both digital and physical glass slides reviews to occur remotely. After the PHE ended, CMS stopped allowing physical slide reviews to be conducted remotely due to the concerns about accuracy and error. Despite this, laboratories can still perform remote reviews on digital materials like slides and test results, provided they follow certain rules. Essentially, the main lab must carry the CLIA certification and must take responsibility for all tests, including those done remotely. As a result, digital slide review will continue to enjoy the flexibility provided during the emergency, while traditional glass slide review will return to stricter rules, with a clear separation between different lab locations. Regardless of the rationale, the current regulation clearly promotes digital pathology, and I'm personally very happy about it. Regarding the FDA enforcement policy for remote digital pathology devices, it also expired on May 11, 2023, and a 180-day transition plan was initiated. After November 2023, digital pathology devices for remote review and reporting of slides previously used under emergency authorization can only be distributed if they are under FDA regulatory review or if manufacturers intend to cease their distribution. These regulatory landmarks underline the delicate balance between innovation and patient safety, a balance that continues to shape the field of digital pathology. Each step represents both a response to technological advancement and a guiding influence on the development and application of these technologies. I know that following all those milestones in an audiobook can be a little bit challenging, so in the PDF, you will find a chronological timeline of all those events and milestones in the form of an infographic that's a lot easier to follow than the same infographic in a written out form. So go ahead, check the PDF, and have a look at the milestones in a more digestible way. Basic digitalization concepts. A. About digitalization, and digital transformation. Introduction to digitalization. In the 21st century, digitalization has become the norm in many industries, including healthcare. To stay efficient, fast, and competitive, you need to go digital. The possibility to go digital in pathology opened with the technology of digital photography, which allowed for digitization of images. This technology was fully embraced by the radiology community, and the pathology world is heading in the same direction. Still a bit slowly, but with every digitized slide, we are getting closer. But what does it even mean to go digital in a pathology lab? In the context of this book, we will refer to going digital as the full digital transformation. A full digital transformation of a pathology lab is a complex endeavor and requires great coordination within an institution. But it can be extremely beneficial to patients, pathology laboratories, and entire institutional departments. The process involves several steps, including digitization, digitalization and digital transformation. In this chapter, we will take a deeper look at these concepts and how they have impacted digital pathology. Digitization currently involves making glass slides accessible in digital form by scanning them. And I say currently because maybe in the future we're going to get to glassless pathology and we will not have to make glass slides at all. But at the moment, it's scanning the glass slides. While digitalization involves using these digital slides for evaluation or other purposes, such as image analysis. Digital transformation, on the other hand, refers to the process of integrating digital technology into all aspects of a business or institution, fundamentally changing how it operates and delivers value to its customers and stakeholders. An excellent example of full digital transformation is IDEXX, a veterinary diagnostic company that underwent a digital transformation in 2014 and enabled pathologists to work remotely and thus scale their operations through digital pathology. Digitization, the scanner and its components. At the time of writing this book, digital pathology is being built on top of analog pathology. It means that tissue is processed, mounted on glass slides, and stained. Only then can it be digitized. Although there is significant research being done on glassless approaches in which the need for physical slides is reduced or eliminated, including fluorescent imaging of unprocessed specimens, almost all of the pathology work is based on H&E stained tissue samples mounted on glass slides. Scanning glass slides to create digital images is the first step in digital pathology. This is known as the digitization step. It is being done with scanning devices called whole slide scanners. Digital pathology uses a whole slide scanner to capture the whole slide image, which involves taking multiple pictures at various magnifications to create a zoomable dynamic image that mimics viewers' experience with a microscope, but on a computer screen. The scanner components include 1. Light source. Illumination is crucial for clear imaging. LED light sources are commonly used because they provide bright, uniform light with good longevity and low heat production. 2. Slide feeder. This is the component where the glass slides are placed for scanning. The capacity of the slide feeder can vary depending on the model of the scanner, ranging from a single slide to hundreds or even up to 1,000, as of the time of reading this book, of slides for high throughput scanners. 3. Motorized XY stage. This component moves the slides in 2 dimensions, X and Y axis, under the microscope objective. This allows different areas of the slide to be imaged sequentially. 4. Microscope objective lenses. This functions as the eye of the scanner, magnifying the sample on the slide to a level that can be captured digitally. Different scanners may use different types or numbers of objectives depending on the level of detail and speed required. 5. Focus drive, also known as Z stage. This moves the objective lens up and down in the Z axis to adjust the focus on different levels of the slide. This is especially important when creating Z stacks or when dealing with tissue sections of varying thicknesses. And by the way, Z stacks are stacks of scans at different levels of thickness. 6. Camera. The camera captures the images as seen through the microscope objective. The camera's resolution, sensitivity, and speed are crucial to the quality of the images produced. 7. Image processing software. While not a physical component, this software is crucial for the operation of the whole slide scanner. It controls the scanning process, stitches together the imaged areas of the slide, adjusts image quality, and compresses the images for storage. 8. Computer system. A powerful computer system is often required to handle the large amounts of data generated by the scanner and to run the image processing software. 9. Display. A high-quality monitor is important for viewing the digitized slides in detail. Each of these components plays an essential role in the digital imaging of histological and pathological slides. And in the PDF, you can have a look at an illustration showing all those components together. Interestingly, several of the scanner components are identical to those found in a microscope, highlighting the reliance on digital pathology in light microscopy. It means that the whole slide scanner is a microscope with an additional capability to produce digital images. And the technology used to produce these high-resolution, high-magnification digital images is light microscopy, the same technology that was used by Antoine Leeuwenhoek to look at protists and bacteria in 1677. And it is the same technology that all pathologists and histotechnologists are trained on. Even though digital pathology is cutting edge, at its core, it's as familiar to a pathologist or a scientist as light microscopy. Let's remember about it when we are saying, oh, we're ditching our microscopes. No, we're just exchanging them for different type of microscopes and looking at the images on the computer screen and not through the ocular. Unlike static digital images that we are used to taking with our smartphones and other digital cameras, whole slide images are very big in terms of data. One whole slide image of a full tissue slide at 40x magnification can be as big as a 2-hour high-definition movie. That's around 4 gigabytes of data. A scanner acquires the whole slide image by taking multiple pictures to depict the full area covered with tissue on the slide. These images are captured at several magnification levels and therefore contain many pixels. Then images are edited, stitched together, and stored in a form of an image pyramid. The scanner performs image acquisition, the scanning, stores the images, edits them, and displays them. The size of whole slide images is so large because they are captured at multiple levels to enable zooming and a microscope-like experience. As we've explored the key components of a whole slide scanner, it's vital to choose a device that aligns with your specific needs, including the type of slides you will be working on and the throughput of your lab. To guide you in this process, we have prepared a comprehensive downloadable list of questions, and you can find it in the blog section on the digitalpathologyplace.com website. Just check for the How to Choose a Whole Slide Scanner article, and you will get the comprehensive guide. And if you're looking at the PDF, there should be a clickable link to this article. C. Digitalization and its challenges, data generation and management. I wish it was all fantastic and roses, but in digital pathology, as much as I love it, you're gonna have to troubleshoot a lot. Digitalization is the process of using digitized images for something useful, such as image analysis or evaluation. As we just described, whole slide images are usually large due to the several images captured at different layers, and one whole slide image at 40x magnification can be as large as 4 gigabytes. This means that if a laboratory diagnoses 5,000 whole slide images daily, it generates 5 petabytes of data per year, which petabytes is beyond my comprehension, and that's why I have to translate it into hours of HD movies, and that would equate to about 64 years of HD movies. The volume of data generated creates a challenge in terms of storage, retrieval, and backup. Additionally, several proprietary whole slide imaging formats create interoperability issues in digital pathology. Storing and retrieving large amounts of data is a significant challenge in digital pathology. And to emphasize again, the existence of several proprietary whole slide imaging formats create interoperability issues, making it difficult to develop image analysis algorithms. The image analysis scientists have workarounds, so they still do it, but I wish just everybody went with one format. For example, DICOM, like they do in radiology. So in pathology, you're going to come across JPEG, PNG, VSI, XML, SVS, VMS, DZI, NDPI, CZI, TIFF, ND2, ZIF, SZI, QPTIFF, and several others, and in radiology, you're going to have DICOM. So computer scientists who work in the field of digital pathology often find themselves frustrated when developing image analysis algorithms due to the numerous file formats that lack interoperability. Pathologists are similarly annoyed by this issue, with formats like JPEG, PNG, VSI, XML, NDPI, and CZI, just to mention a few, causing confusion and difficulties. In contrast, radiology uses DICOM, which stands for Digital Imaging and Communications in Medicine. This standard was developed by American College of Radiology, ACR, and the National Electrical Manufacturers Association, NEMA, to facilitate interoperability of systems dealing with medical imaging. DICOM format supports a wide array of medical imaging types, including CT, computed tomography, MRI, magnetic resonance imaging, ultrasound, X-ray, and more. It not only stores the image data, but also associated patient and procedural information, making it a comprehensive and standardized solution for medical imaging needs. The adoption in pathology has been limited so far. This is due to several reasons, including the lack of scanners that produce DICOM native whole slide images, although there are some coming out in the market as I read it. The challenges associated with retrofitting existing PACS, picture archiving and communication system infrastructure to accommodate large whole slide image files, and the initial absence of viewers capable of handling DICOM formatted whole slide images. However, the push for fully digitized workflows in pathology departments is increasing, and with it, the need for standardization in digital pathology image formats. Therefore, despite the challenges, there are ongoing efforts to promote the wider adoption of DICOM in pathology. Because we are still at the beginning of the digitalization journey in pathology, it means that users can actively contribute to shaping this landscape. Vendors are key players in the process, and it is within their remit to incorporate the DICOM standard in the development of their products. As consumers and end users, your input holds significant sway in driving vendors' product design and development. Hence, I encourage you to take an active role in engaging with vendors about the need for DICOM integration or any other unmet needs that you might have regarding your digital pathology operations. Just let them know you want it. By demanding DICOM capabilities and other needs that you might have, you will not only enhance your own workflow, but also contribute to a broader push for standardization in pathology, paving the way for improved interoperability and overall advancement of the field. D. Digital transformation is the next level after digitalization, and it can involve not only the digitization of all the slides used for diagnosis, but also using image analysis and artificial intelligence for decision support, both of which can lead to changes in the business model. IDEX, a veterinary diagnostic company, for example, underwent a digital transformation in 2014, where it introduced digital pathology, enabling pathologists to work remotely. This was a game changer in the industry and enabled the company to hire multiple pathologists at multiple locations and scale their operations. The recent 2021 clearance of the prostate cancer decision support system created by the company Page AI that uses AI-based image analysis is an example of the next transformation step. The system increases pathologists' efficiency by leveraging AI and image analysis to point out areas suspicious of malignancy to the reviewing pathologist. The validation studies of this decision support software showed that pathologists supported by this AI tool can diagnose prostate cancer faster and more accurately than pathologists without the AI tool or than the AI tool alone. This proves that digital pathology can improve efficiency and accuracy and produces the tremendous advantage of remote access to pathology services. However, there are challenges associated with the adoption of digital pathology, including the need for infrastructure, standardization, and training. Also, navigating the regulatory landscape of digital pathology, including the need for regulatory approval of AI algorithms and regulatory compliant validation of digital pathology systems, is a significant effort. E. Unveiling the future. Are pathologists at risk in the digital age? As we finish looking into the topic of digital transformation in pathology, it's essential to address a concern that naturally surfaces as a result of the changes we've discussed: the potential impact on jobs within the field. Are we going to be replaced by AI? This topic is one that carries a substantial amount of weight and anxiety for many pathologists and pathology professionals. The advances in technology and the automation that it brings certainly spark questions about the future of the profession. To delve deeper into this topic and offer a thorough, balanced perspective, I'd like to include a blog post I penned in 2019 when these concerns were beginning to come up more prominently. This post provides a description and exploration of an industry shift that happened after the first deep learning solutions,
More on this in the chapter about image analysis in AI, we're starting to become successful. Surprisingly, the new trends reverted back to fully embracing the role of a pathologist in the digital pathology transformation.
Thank you so much for listening. I hope this is resonating. I hope this is good info, that you are getting value from this first chapter. The first chapter is a little bit longer, so tomorrow is going to be the second part of the first chapter. But before I release the second part of this chapter and the rest of the chapters, could I ask you a favor? If you could grab the PDF from the show notes and take some kind of selfie with you and this PDF on your computer and post it on LinkedIn or Instagram or wherever you most often post, and just tag me, I would very, very much appreciate that. That's going to help me bring the digital pathology knowledge to more people, and it's also going to help me be more connected to you, because I am a fan of my digital pathology trailblazer tribe, and I'll be thrilled to see you tagging me on social media while reading this book. And of course, if you get the physical copy, I just ordered 4 author copies for myself, just to check if they don't look crooked or something before I order more. And then I'm going to be posting also with the physical copy. If you have one, please take a picture and let me know, tag me on LinkedIn. I will be so grateful. And I talk to you in the next episode.